Hello and welcome to this tutorial on CrCEST from the Center for Advanced Metabolic Imaging and Precision Medicine at the University of Pennsylvania.
In this presentation, I'm going to tell you about the different equipment we use in measuring CrCEST at our facility. We're going to show you how maximum voluntary contraction is measured on a subject. We will go over the scanner and patient setup, which is important for getting repeatable data. Then we are also going to show a scan demonstration from the 7T computer, and afterwards a software demonstration in MATLAB will be shown on processing the data.
Let's now look at the equipment used. The equipment shown on this slide displays the various products that are used to assure accurate MVC measurement and CrCEST data acquisition. I will now go into more detail on each of these products. The first product is the load sole from Novel Electronics. This is a sensor that measures participant force in newtons during the plantar flexion MVC measurement and quickly transmits the information to a Bluetooth device such as a phone. An app must be downloaded and more can be read on their website. This load sole is portable and can be positioned against any rigid surface to measure the force generated from the participant. As you will see in our video, we choose to place the load sole in the ergometer. However, any rigid surface can be used. The ergometer we use is the TriSpect model from ErgoSpect Medical Technology. This is an MRI compatible device. We use this device for both the MVC measurement, which is performed out of magnet, and also for the in-magnet plantar flexion exercise. This ergometer also comes with a vest and two straps which fasten the participant to the ergometer. The straps and vest are necessary for accurate MVC measurement because they ensure the participant's body is not displaced in the opposite direction while contracting their gastrocnemius. After the MVC measurement has been taken, the ergometer will be moved to the scanner room and pressure will be applied to the ergometer. In the demonstration to come, we apply 10% of the participant's MVC as force for exercise. The scanner utilized in this demonstration is a 7T Magnetom Terra from Siemens. When in the scan room, we will position the single transmit 28-channel receive phase array coil from QED on the scanner bed. The participant's calf will be positioned in the center of this coil in both the medial lateral and anterior posterior directions. Furthermore, the thickest portion of their calf will be positioned at isocenter. Lastly, some additional equipment used in our setup for MVC measurement are an air tank, two air hoses, and a vacuum pump used to suction the ergometer to a flat surface. For scanning, we utilize dielectric pads, which are from multi-wave imaging. These are used during scanning to help mitigate B1 inhomogeneity. The benefits of the dielectric pad are demonstrated in our work. Again, here is the equipment we utilize for our MVC and CrCEST measurements, and we want to now transition into a video showing how we measure MVC. So, we're going to do the MVC, maximum voluntary contraction, portion of CrCEST right now. We're going to measure your MVC, and then when we do our exercise, we'll be doing 10% of that. All right, so first I'm going to turn on the load sole so that it connects to my phone, and then through the load sole app, we will have connection. Okay, it is now connected. So please put your right foot in. Okay. You're going to strap around the ankle. You can keep your left foot straight. Okay, so what we're going to do is a plantar flexion exercise. You're going to be pushing down through the ball of your foot, and you're going to be using your calf muscle primarily. When you're pushing through your calf, sometimes we want to lift up our hips. Yeah. We want to avoid that right now. So make sure that your hips are planted and that you push solely through your calf. Before we get started, I need to both apply the pressure fully. So I'll apply the pressure and set this to max. That way there won't be any displacement in the ergometer. And then I have to turn on this vacuum so that the ergometer does not move. So we'll connect the vacuum. We'll give it about 10 seconds for the vacuum to suction. Okay, so it's really important that when you're doing the exercise, you're going to push through the same portion of your foot each time. Try to push through with the ball of your foot and make it as repeatable as possible. The same thing goes in the scanner. Remember what portion of the part of the foot you're pushing through, and you're going to do that when we're in the scanner as well. Now, we're going to do 5 bouts where you're going to push as hard as you can through the ball of your foot. I'm going to say ready, set, go. On go, you're going to push as hard as you can for 5 seconds and then stop. We'll repeat that 4 more times. And then in the app, we're going to discard the max and the min and take the average of the 3 in the middle. I'm going to 0 the sensor right now. So we're going to start. I'm going to start the recording. All right, you can push. Ready, go. 2, 3, 4, 5, stop. And we're going to repeat that 4 more times. Ready, set, push. 2, 3, 4, 5, stop. Ready, set, push. 2, 3, 4, 5, stop. 2 more. Ready, set, push. 2, keep going. 3, 4, 5, stop. Ready, set, push. 2, 3, 4, 5, stop. Great job. Okay, so we're going to save that as an ASCII, and then we can look at the data afterwards. We can shut this off. Turn off the pressure, and that's it. Okay, so we're going to be explaining the CrCEST exercise right now. So what I did is I applied 10% of your MVC to this ergometer. So right now, could you push all the way down and then come all the way back up? Great. You could stop. So what I did is I made sure to put on an ankle brace. I put on the ankle brace that helps prevent the ankle moving in the medial lateral direction. Now, this ergometer, as I said, is at 10% MVC. We're going to do 20 compressions per minute for 2 minutes. I'll play an audio recording that will come on through the intercom. It'll come on through the intercom, and it'll say push, release, push, release. That's how you're going to know when you can start your exercise. So right now what I'm going to do is I'm going to make sure that the calf is placed in the center of the coil. We already have pads placed underneath his calf, raised up, so his calf is already at isocenter in the anterior-posterior direction. Next, I want to place the coil. I want to adjust the direction of this coil so that now his calf is in the center of the coil in the medial lateral direction. It is. You can also see we have a dielectric pad right here. This is going to help the B1 in homogeneity. For the scan, we're at 7 Tesla, so that's more important. I'm now going to put pads on top to ensure that his calf will not move. And I will sandwich the coil. Good. Keep going. So it's very important that when you're exercising, you're going to push through the ball of your foot. You're going to make it as consistent as possible. So try and push through the ball of your foot each time, whenever you hear it, and make it as repeatable as possible. Also, as a note, we have 2 hoses connected back here. One hose is for the air pressure, the other one is for the vacuum. The vacuum is going to prevent this ergometer from getting displaced during his exercise.
Here we will show the basic steps necessary for the CrCEST acquisition. This scan is being performed on a Siemens 7T Terra scanner. First, we will acquire the triplane localizer, and from there, we will take a multi-slice acquisition to find the thickest part of the participant's calf. We see that the thickest slice of the calf is not necessarily at isocenter, but is more superior from isocenter, which may result in a poorer shim. If this were a volunteer for a clinical study, then this placement would be unsatisfactory. However, for the purposes of this video, we will continue. I also want to point out the placement of the dielectric pad. It is clearly seen by the lateral gastrocnemius muscle of the participant. This dielectric pad helps mitigate B1 inhomogeneity.
Now I am placing the 2D none image on the thickest slice of the participant's calf, and then I adjust the shim volume to match the field of view and start the process of shimming. After I spent a few moments manually shimming, the best shim I achieved is 42 Hz. Our aim in shimming is always to have a full width half max of 40 Hz or less. This elevated shim of 42 Hz may be due to the shim being a few centimeters from isocenter. Recommended next steps to improve the shim would be to use the 3D shim function about 3 times, adjust the center frequency, and then perform manual shimming again for a few minutes. Furthermore, we have found that participants with large amounts of adipose tissue around their muscles often lead to more difficult shimming. The next steps are to run baseline creatine CrCEST. We will run the none image, which is a reference image, and then the B1 map, the B0 map, which is the Wasser, and the creatine CrCEST acquisition. In this display, the arrow with the number 4 and the subsequent 4s beneath it signify that the slice and adjustment volume has been copied. So if this feature is not enabled on your scanner, then ensure that you copy the slice and adjustment volumes. Here I am looking at the B1 image. I want to make sure that the image is not oversaturated at any of the variable B1s that are used. I want to ensure that the image is not oversaturated, and I do this by ensuring that the windowing can adjust the image to be completely black. If there is oversaturation, this may be due to a suboptimal reference voltage or image scaling factor, so the voltage or image scaling factor should be adjusted. Here I want to look at the Wasser image and ensure that the first image has the least signal intensity. This is where the frequency offset acquired is placed on the water frequency. Then, each pair of subsequent images should get brighter and brighter since the offset is moving further and further away from water. Also, you should check to ensure there is no motion. Then I look at the CrCEST acquisition and ensure that the image contrast varies with each offset. I also want to ensure that each of the measurements has a similar contrast across offsets since they are all baseline images. You should also ensure that the image is not oversaturated for each offset and that there is no motion. The next step is to perform the mild plantar flexion exercise. Before starting exercise, ensure that your slice and adjustment volume have been copied for the post-exercise steps. You should also take a moment to reopen the shim settings and verify that the shim is still less than 40 Hz and that the center frequency is at 0 and that no drift has occurred. Next, it is at this point you want to remind the participant to keep their hips as still as possible to avoid additional displacement of the leg in the coil. You also want to remind them that their exercise should be as consistent as possible. Remind them to focus on pushing down with the ball of their foot, and with each contraction, they should repeat pushing in that same region. Although seemingly menial, this step helps ensure repeatability within subjects and provides a controlled exercise for each participant. Furthermore, the audio file we created is attached in our documentation. Push, release, push, release, push, release, push, release. Now that it has nearly been 2 minutes, we want to ensure that we start our acquisition as soon as the last contraction has been performed and their foot is at rest. This is essential because each creatine CrCEST measurement takes 30 seconds and the typical recovery for a healthy individual is less than 2 minutes. So acquiring the first data point as soon as possible is essential. Also, you may see in our video, our post-exercise acquisition is only 30 seconds. This is because we only acquired one measurement in this demonstration, but typically we acquire 15 or 16 measurements to ensure we track the creatine CrCEST recovery all the way back to baseline. We then ensure that the slice and adjustment volume are copied and then run the rest of the protocol. One should also look through the post-exercise CrCEST, none, Wasser, and B1 images to ensure that the participant did not have significant movement during acquisition, and one should also consider the points made earlier in the video for the CrCEST, Wasser, and B1 images.
Okay, so this is the software demonstration for the creatine CrCEST code. We'll be able to run it by loading the app. And it finds the parameter file
If it does not find the parameter file, there will be a box that will come up and you could select this parameter file that is also on the GitHub. We'll select the directory for where our data is. And it will auto find the files of interest for the reference, B0, B1, and CrCEST for pre and post exercise. There is an option to deselect Wasser if you have an alternative B0 correction. In this code, the alternative is a phase-based B0 correction. We're going to use the Wasser though. We can see we can also adjust parameters. I'll adjust the B0 tolerance to 0.1, and I'll adjust the filter so that we have a stronger filter. Let's go to read and calculate. The first question is to select regions to exclude. You do not need to do this. I will just select one for an example. So this region will be excluded in the processing of the data. And then it asks you a second time for the post-exercise acquisition. We'll keep the same region. Now it's just processed the data. Now we can look at the CrCEST maps. You can see that it looks very filtered. You can see the image is smooth. The first 4 images display the pre-exercise. We had 4 averages of the pre-exercise CrCEST. And then we see the time scale of the post-exercise creatine CrCEST, how it recovers back to baseline over time, with each of these images being 30 seconds apart. Also to note, if we want to unfilter the data, we just have to recalculate. This time I'm not going to select regions to exclude. It gets reprocessed, and we can see that the image is no longer smoothed, and the image, look, you can see the individual pixels much better. We can also look at the B1 for pre and post, the B0. And then in order to do calculations on the ROIs, we need to assign the number of ROIs. Currently, in the params file, the max number is 4. You could add more muscle groups if you'd like to in this parameter file. We're going to work with 4 right now. So we'll select ROIs. This will populate the pre-exercise acquisition first. So it tells us to choose the lateral gastrocnemius, the MG, the soleus. Now that I just selected all of the pre-exercise, it will now tell you to do that for the post-exercise. It auto-populates what you drew in the pre-exercise, so we see that there was a little bit of movement in the subject. I can adjust the MG, the soleus. Now that we've drawn our ROIs, we can now select to view the time series. We see that in this image, there's each color coordinates with the plot. So we can see it for the MG, the LG, the soleus. We see the increase, the recovery time in seconds is plotted, the baseline is plotted, and then voxels pre and post exercise are also shown. The voxels pre and post exercise appear to be similar in 3 of the 4 muscle groups. We see that in the LG, there is a variation. This is a minor variation, which is due to different thresholding pre and post exercise, and also because the segmentation was moved slightly pre and post exercise. We can close these. These can be saved if you select the print button. Reference ROI just displays the image of your segmentation pre and post exercise, and the CrCEST weighted images can also be analyzed. Register is a feature that is not yet active for our program, but will be in the future. We have the ability to save the data and export it as well. The function change directory allows you to manually change any of the directories that were automatically read in, and you could select a directory in place of this. At the top, we can see that there are 4 other functions: load, which loads previous data; clear, which will clear this data set; save, which will allow you to enter a note; and lastly, export, which would allow you to save your data as a MAT file, and it is also exported as a CSV file.